Okay. So when we look at these, we should have noticed that if we add something to the end of the function, what does it do when we're graphing? So if we take function, not just the absolute value, but if we deal with any function, f of x, and we add something to the end of it, what would that do to the graph? And what it's going to do is shift it up that many units. Okay? So I would like you to add this general notation up above here. Just like I did, I want this general. And two reasons. One, it helps us understand it works for any function. And two, this is the notation that I've seen on the SAT.
I'm taking that thing.
Are you good? Many of you will have probably signed up to take the PSAT in 2 weeks.
But I'm kind of scared.
Wait, what day?
I'm going to miss a lot.
It's Wednesday.
Are we going to have this class?
You will miss first, second, and third period.
I don't want to.
Why did I not do that?
I don't want to.
All right.
You can still sign up.
Okay.
I'm gonna pass. I don't want to pay taxes.
Why would you pay to take a test?
So you get better for when you really
The
count.
real SAT costs about $60,
I paid
and the PS costs what, 15?
20.
Okay,
That's not
20.
even fair.
So what it is it's cheap practice for the real thing.
But what about
Is the real thing free?
No, the real thing is like $60.
Well, what about if I can't afford to take it?
Okay.
So you have to pay for something you don't want
called
to do.
gambling. If you get
I'm
good
done
grade,
here.
it could be $1 million.
Pay for everything.
Oh, you don't have to do it. You don't have to go to college.
I like it.
That's good.
Oh,
That's right.
you pulled that one.
If you take it as a freshman, do you still have to take it as a sophomore?
Every student will take it as a sophomore. The state pays for that unless they change the payment of
So
that.
then it's free.
Next year, you can take the PSAT at no cost if the state doesn't change its policy. It has changed policy in the past, so we'll see. All right, the second one. The first graph is the red one, and then shifted down 3 to give us the blue one, and it shifted the red one down 7 to give us the green one. So hopefully you noticed it was shifting the function down 3 units and then again 7 units. So if we take a function, this is a different function this time, but if we take a function and subtract something from the end of it, that's going to shift our function down, whatever A is units. So if we add or subtract to the end of a function, it causes a vertical shift. If we add something, it causes a vertical shift up that many units. Subtract, it causes a vertical shift down that many units. And that's what we were hoping you could get out of 1 and 2. Any questions about those two? Okay, let's look at the next one. All right, so the red one was the first one, and then the blue one was the second one, and the green one was the third one. Do you see how I used 3 and 7 over and over and over again? Well, did you notice that this time it shifted it left 3 units and then left 7 units? So hopefully we noticed if something is grouped with the x, if we have something added to the x that's being grouped with it, that will shift the function left that many units. So if you don't have this written down, please write that down now.
Is there a little square root on top of that thing?
Evan, do you have yours?
I do not. I left it in another binder. It's not with me right now. I know. Not open.
I mean a little square root, or am I just being
A square root?
Yeah,
When?
on the square, like
On this one?
Yeah.
Oh no, I was just saying in general for any function. That's why it's in terms of f of x instead of in terms of a function.
No, like
There's no square here if I'm talking in terms of f of x.
I'm confused.
Okay, the next one, we were subtracting things, and instead of shifting left, what did it do? It went right. So this shifted it right 3 units and right 7 units. So, different function, this time square root function. It shifted the square root function right units and then right 7 units. So if we have something subtracted from our x that's being grouped with that x, it actually shifts the function right that many units. Now this is kind of awkward to me. It's weird how this works. Because when I think x, if I saw like like in the first one, a positive x, doesn't that usually mean right?
Yeah.
And when I saw on this one a negative, doesn't that usually mean left?
Yeah, that was
Yeah, that
When,
was
when it's grouped with the x, it always does the opposite, whether it's added or subtracted or whether it's multiplied or divided. When it's grouped with the x, it does the opposite. So when we have the plus 3, that actually sent it left 3. And when we have the minus 3, that actually sent it right 3.
It's kind of when you're driving a car backwards.
Maybe.
Turn to the right, it's going left.
Yeah.
Oh, that's like a boat. Right?
Well, I'm talking about driving a car backwards.
I mean,
I was talking about a boat though.
It's like the thing where you go.
You mean he's driving the car?
I hate driving boats backwards.
It's not like a boat with a steering wheel. It's, yeah.
It's like the stick.
Yeah, the stick in the back of the
Paddle
boat.
boat.
You do it backwards.
It's not
Yeah.
a paddle boat.
You know, I don't even care.
Okay.
It's
Alright, this one is square root once again. But the red one was our first one and the blue one was the second one. Did you note that it was a reflection of the y-axis?
Yes.
And then the green one was a reflection that got shifted. It's a reflection of the y-axis that was shifted up 3 units. So, when we had a negative inside our grouping symbol with our x, it changes all the x's to the opposite. And when it changes all the x's to the opposite, doesn't that fit over the y-axis? Yeah. So a negative inside with the x is going to cause a reflection over the y-axis. Do you have that written down?
I'm currently writing it.
Okay, versus the next one. The negative was out in front. It wasn't inside with the x. It was out in front. And when the negative is out in front, it changes the result to the opposite. So basically it changes all your y's to the opposite. And when we change our y's to the opposite, that reflects it over the x-axis. So the absolute value, which is the next one, the negative out in front is causing a reflection over the x-axis. So whenever we have this negative right here out in front, reflect over the x-axis. Any questions?
The way you graph that with all the colors and everything looks so trippy. Number 6.
Okay, the next one is interesting. And I keep losing my rubber band. Thank you.
Those are the answers.
Okay, I'll get another one. Alright, so the next section is on vertical stretches, compressions, horizontal stretches, and compressions. So what I'm going to do is I'm going to show you my rubber band. There we go. Now, what happens to the rubber band as I vertically stretch it or pull it?
It goes.
Did it get skinnier? So it went from that, and then when you stretch it, it gets skinnier, right? So that's what happens here too. When I pull, when I vertically stretch this graph, it went from the red one to the blue one to the green one. The more it's stretched, the skinnier it becomes. That's a vertical stretch. So, when we have a coefficient out in front, an a out in front, a times f of x, if that a is greater than 1, that's going to cause a vertical stretch by a factor of a. It stretches it vertically by a factor of a. Okay, versus the next one. The next one I'm multiplying by something too, but this time I'm multiplying by a number that's less than 1. So between 0 and 1. Now this causes a vertical compression. And when I take my rubber band and I squish it vertically, what happens to it? Whoops, it got wider. So the same thing here. When I pull it this way, when I pull horizontally, it gets wider. When I compress, pull horizontally is in just a moment. When I compress, it gets wider. So a vertical compression by a factor of a. Now, some of you may have heard this called a vertical shrink, and that's acceptable, but I always use the word compression because it's really in one direction. It's vertically pressing down. When I think shrink, I think get smaller in every direction, like shrinky dinks. Did any of y'all have shrinky dinks when y'all were little and you put them in the oven and they shrunk and it made your big picture get really small and the colors got bright and it was lots of fun? Yeah? Okay, so when I think shrink, I think about shrinky dink, shrinking in every direction. But that's not what this is. A vertical compression is just in one direction, vertically. So that's why I call it compression instead of shrink. But other teachers will call it shrink, and it's not wrong. All right, this one. This is horizontally. If it's in with the x, it's a horizontal. This one made it wider, just like this one made it wider. But this one made it wider vertically, because I'm pressing down and it vertically got wider, versus this one's going to make it wider by stretching horizontally. Still gets wider. This one got wider by stretching, pulling horizontally. This one got wider by pressing vertically, compressing vertically. Okay, so if something is in multiplied times the x, if that number is between 0 and 1, then that causes a horizontal stretch by a factor of 1 over a. That's just reciprocal, right? So do you see that this one is being divided by 5?
Yes.
So isn't that the same as multiplying by a fifth?
Yeah.
So we would call that a horizontal stretch by a factor of, what's the reciprocal of 1/5? 5. That's a horizontal stretch by a factor of 5, right? Were you thinking about the baseball series coming up?
No.
You got
I'm
tickets
going
to Braves?
Friday.
So is my husband and my son
Really?
and grandpa.
They're gonna lose.
No, they're not. Okay, they might lose one game.
Downer.
Matt,
No,
Matt.
there's.
seriously.
You might not be a fan of the Braves, but you know it would be cool
The
for an
Red
Atlanta team
Sox
to win the
are,
World Series.
you know,
Oh,
Again.
yeah,
Okay.
Yeah, the Red Sox are gonna, obviously.
All right. Sorry about that. We're off topic slightly. But go Braves. It's really Ryan's fault for daydreaming. All right. Now, last problem. Last problem is a horizontal compression. A horizontal compression. Now, doesn't a horizontal compression and a vertical stretch look alike?
They kind of do.
Yeah, because when I squeeze this way, it kind of has the same look as if I pull this way. And just like a horizontal stretch and a vertical compression look similar. And on some functions, they're more than just similar, they're kind of the same thing. But on other functions, they're just similar. Gotta be careful what function you're dealing with. All right. So this one is a horizontal compression, and we get a horizontal compression when what's multiplied by our x is greater than 1. Because when it affects the x, we always do the opposite. And we'll go over this in detail as we go through our transformations. Now, did I expect you to completely understand everything you did yesterday? Nope.
Not one bit.
Yesterday was dipping toes in the water. Okay, today we're going to start learning how to swim. But we're going to just take it a little bit at a time. We have 3 different types of transformations to do in this section. We're going to do translations, which is our shifting, up, down, left, right. We're going to do reflections over the x and the y. And we're going to do vertical stretches and compressions.
I remember last year we did rotations in regular math, and I would always forget the formula. Like every single time.
No, that is homework next week as we review for our test. So, yeah, the back of last night's packet is homework for next week. For those of you that may have misplaced it, I'll put a copy of the homework on my website for next week. You may keep the quiz. Yeah. I did yesterday for
How big is the packet? Maybe it is
Okay.
Or you could say it is on
translations. So we're going to do vertical translations and horizontal translations. So what we should have been introduced to yesterday, yes ma'am? Y'all didn't get one? Anybody get two?
You got extra. You got it. You got it.
Might have this really extra. Yeah.
You only got one packet? Okay. Alright, here we go. If anybody finds the next one to the back of theirs, let me know. Alright, some of you are looking at the packet and panicking. That packet is for the next 4 days. It's not all tonight, okay? 4 days. So, let's get going. Alright, today, once again, we are just studying translations. It's a rigid transformation. It's going to change how the shape looks. It's just going to move it around on our coordinate plane. So, what we learned yesterday by using our graphing calculators is if we add or subtract something to the end of the function, that's going to shift it up or down. If we add or subtract something to the x, that shifts it left or right. Now, a translation is shifting a graph up, down, left, or right without changing the shape of the graph. So the first graph we're going to start with is y equals x squared. And what I've done is I've already created a table of values by plugging x values into this function and getting out y values, and then I graphed it for you. This is called the parent function. And this parent function is actually a quadratic function. And we're going to study this in detail next year. You don't have to know the name quadratic function right now. I'm going to use it just because I'm a math teacher and I like to use proper terminology. But you don't have to know the name. And you don't even have to know these points, but you do have to know how to shift it. So this is our first graph, the quadratic function, y equals x squared. Now, we're going to prove to you that what we learned yesterday in our calculator lab is true. What do you think is going to happen to that parent graph?
It's gonna go up.
Shift up too.
Yeah.
That's what you think is going to happen. Okay, so let's see if that really happens. We think it's going to shift up 2 units. That's what we think. Well, let's see. If we plug values in, if we plug in -3, -3 squared is 9, plus 2 is 11. -2 squared is 4, plus 2 is 6. -1 squared is 1, plus 2 is 3. 0 squared is 0, plus 2 is 2. 1 squared is 1, plus 2 is 3. 2 squared is 4, plus 2 is 6. And 3 squared is 9, plus 2 is 11. So if we plot these points, -3, 11. -2, 6. -1, 3. And then 1, 3, 2, 6, and 3, 11. Did that take my original function and shift it up 2 units? Okay, so do we see how if we have the parent graph, it's a lot quicker if we just took every one of those points and moved it up 2 units than creating this whole new table. Okay, let's just verify that it works. If I do complete the table for the next one, -3 squared is 9, minus 2 is 7. -2 squared is 4, minus 2 is 2. -1 squared is 1, minus 2 is -1. 0 minus 2 is -2. 1 minus 2 is -1. 2 squared is 4, minus 2 is 2. And then 3 squared minus 2 is 7. So if I plot these points, 3, 7, -2, 2, -1, -1. Did it take that parent graph and just shift it down
It did.
2 units? So this is a vertical shift. down 2 units. And you could just say shift down because the down part explains the vertical. So if we add or subtracted anything to the end, we don't really have to do this table. We just take our points and move them up or down. Are we good?
I'm good.
Okay, now let's look at the next transformation. All right, so let's do the chart on this one. Do you see how I picked different numbers? I didn't go -3 to +3.
Yeah, because then if you did like,
Because it wouldn't give me a nice shape of my graph if I did. I know where it needs to be, so I gave you numbers that would work nicely. If I plugged in -6, I'd get out -3, and -3 squared is 9. If I plug in -5, +3 is -2, -2 squared is 4. If I plug in 4, -4 plus 3 is -1, squared is 1. Plug in -3, you get out 0, squared is 0. Plug in -2, you get out 1, squared is 1. Plug in -1, you get out 2, squared is 4. Plug in 0, you get out 3, squared is 9.
how about that?
So it did turn out nicely. Wait, that's not 9. 9's up here, isn't it? 4, 5, 6, 7, 8, 9. There. Okay, so adding 3 here did what? It sent it left 3, didn't it? So remember, whenever it's grouped with the X, we always do the opposite. So maybe this looks like I should go right 3. But in reality, we just showed that you must shift left 3. If it is grouped, you do the opposite. And you can see why.
Learn something new every day.
Yeah. Okay. All right. Ooh, the absolute value. What's the graph going to look like?
Oh, it's gonna be the.
Yes, it is. It's going to be the V. Because the absolute value of -3 is 3. The absolute value of -2 is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. 1, 1, 2, 2, 3, 3. So when I plot those points, it does make the V.
Hashtag voice crack.
Don't crack
Okay, so we're going to do this one backwards. We're going to draw the graph and then see if the points match up with what should be in here. So what does this tell me to do?
Add 2 to the X.
Well, to the graph. I'm sorry, to the parent graph. What should I do to the parent graph?
Move left 2
Shift left 2 units.
digits.
Okay, so let's do it. Let's take this point and shift it left 2. Let's take this point and shift it left 2. This point and left 2. This point and left 2. This point left 2. Every point gets shifted left 2 units. And that's what my function looks like. So let's prove that this is what it's supposed to look like. If I plugged in -5, -5 plus 2 is 3. Is there a point at -5, 3? Yeah. If I plugged in -4, -4 plus 2 is -2. The absolute value is 2. Is there a point at -4, 2? Yeah. Do you see how just moving it actually gives us the same things that filling out the whole data table would? Plug in -3, you get out 1. Plug in -2, you get out 0. You get 1, you get 2, you get 3. And that's what just shifting did for us. We do not have to do the table. Yay! Don't do it. Don't. Here we go. Do it. Okay? So I want you to try this one without using the table. Can you do this without using the table?
I bet you I can.
Good. Do it.
I can momentarily dance before.
So don't even check ourselves with the table?
Don't even check yourself.
Don't even. Like,
I think you can do it.
Easy peasy.
Are we doing it based on the original graph or one above it? Spencer. This will look already finished.
E and Z.
Alright, because we never watched. I never did that.
Because I'm just trying to go to the fourth dimension.
I didn't pull away.
Yeah.
Okay. Did you go right 2 and up 1?
Yes, I did.
Right 2 and up 1. That was kind of funny.
That was
I
bad.
didn't even hear it.
Boom.
Okay, that one.
Alright.
Okay. Alright, right 2 and up 1. Right 2 and up 1. That just reminded me I shouldn't give my son high fives as he gets older and stronger. Oh, sorry. Alright, right 2, up 1, new function. Boom, boom, boom. And we're done. It's very nice. It goes fast. And it's easy. We got it?
I got it.
Alright, so it should look like that. It's a horizontal shift, right 2, vertical shift, up 1, and you don't have to use the words horizontal and vertical. Sorry? Okay, next function, another new function. This one is the square root function. Why did I pick 0, 1, 4, and 9? Because they are perfect squares and we can take the square root of them. Well, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. I don't know what I'm writing. Let's try making a 3. So we plot these points. Sorry about this graph being a little tight. It's a little hard to find the points.
It's alright. It's alright. Alright, alright, alright. Sorry. Oh, well. Sorry.
All right.
You don't have to judge me.
There's our parent graph. So we do not have to make a table now. We've got a graph to work with. What does this do to this graph? Okay, Ryan?
It shifts it over 2.
No, this one.
That shifts over 5 horizontally.
Downly.
Right.
Downly.
Downly. Oh.
Obviously down.
Okay, he knew until I called on him. It's a shift down
Yes.
5 units.
It's okay, Ryan. We all make
Okay, so all we're going to do is we're going to take this graph and we're going to pull it down 5 units. Do it.
Boom.
Oh, hey, cheater at it.
I did cheat. Ta-da! Down 5 units.
I can't see them. I can't tell where I'm at. 1, 2, 3, 4, 5, 6, 7, 8.
It's the next to the last one.
Thank you.
Matt.
Sorry.
Oh, no, other Matt. You can keep singing that. I mean,
Thanks, Ron.
go
for it.
it's busting
Wait.
out.
I didn't hear what he said earlier. What did he say?
Hey, nothing.
I was calling the other Matt.
I think you should sing. You're recording this, right?
I am recording it.
So should I get like a little bit of music to do the
Well,
work?
background music to my. I have background music every
even
day in
Jeopardy
this
has
class.
background music.
All right.
What background?
So, how'd you do? Does yours look like mine? Okay, it's about to go away. Look carefully. Gone. All right. Now, next one. What are we doing with this one? Raise your hand if you know, and if I can remember your name, I'll call on you. Kyle had his hand up first.
Shift to the left.
Shift
goes,
left.
And
Yes.
shift down, up,
Left 2 units and up 1.
I could only have said it a little bit better myself.
Okay, so that's all we gotta do. We gotta take these points and do that with them. Left 2, up 1, boom.
I want something like that, so I don't have to redraw it.
Over and over again, isn't that
Yeah,
right?
it's really hard to do work. I hate doing work.
Can we actually get one of those to test? Just
That would be
like
cool.
stickers, just stick them on the right place.
These are all good ideas.
I think you should invest in that.
I'm trying to think of a song.
No,
that does
I'm
this.
thinking somebody needs to write a program
Oh,
that,
and up.
that I can move things around like this
Down two.
in a testing situation.
Just killed a man. What I've done against his will.
Did you do it?
Yes, I did.
You did this one?
Oh, I did the other.
No, I was fixing to say I see nothing on your paper.
No, it's right there.
Okay. So it should have looked like that. Those two. Yes. Good. All right. Let's move on. Describe the transformations on this graph. Now we don't know what it looks like. Okay. I know. Y'all may not. But we know what this does to this graph. What does adding 4 to the x do to my parent graph here? Left 4. Shift left 4 units. I left out the word shift. Okay, what does this do on number 4? Shift up 1 unit.
Alright, we move on.
Okay, now this is in terms of any function I pick. Y equals any function Miss Willoughby feels like giving us, f of x. What would happen if I did this to it?
It would go up 3.
Go
Yep.
for units.
Shift up 3 units.
Up. 3.
Oh,
And
I
what
know.
would this do?
Right,
Right,
8,
eight,
down
down
1.
one.
Right 8 and down 1.
Dude, this is legit.
Okay, speaking of any function Miss Willoughby wants to use, here's one. Okay? Y equals f of x, and it's this picture. So,
Wait, are we supposed to write this? Oh, I see it.
you've already gotten it. So, there's my picture. So, point right here, point right here, point right here, point right here. Connect the dots in between. That's what I'm dealing with.
Oh, it goes.
All right, what would this do? F of x plus 3.
It would go. It would go up 3.
It would take every point and shift it up 3.
Oh, come on.
Just completely cheating here, aren't I?
Well,
Oh, I
it doesn't
didn't do
work
it.
because there's
Hold
a.
on.
It,
Oh, it's smaller.
yeah.
Man.
Dang it.
Yeah.
You gotta do it on your own.
Well,
Yeah.
doodle.
No, I don't. It's already done.
Oh, she landed.
All right. So what would this do, guys?
That would go right.
Right 5. So could you do this? Could you individually move each little point?
Absolutely.
Yes, you could. You're individually taking these 4 points and shifting them up 3 and connecting to the dots. You're individually shifting these 4 points back, to the right 5 and connecting the dots. That's all you're doing. Does that make sense?
Yes.
Okay, the top of the next page gives us 2 more, but we don't need them. What I do want you to do is write, what would it be? What would I have to do this transformation?
Left 2, down 4.
Left 2, down 4.
And then the other one would be right 3, down 2.
So these are shifts.
Oh, we use graph paper?
What?
Oh.
Wrapping paper?
Okay, now this is your homework. 1 through 4 can be done on here. I either want you to use different colors, or when you graph them, I want you to number them 1, 2, 3, 4, so we can clearly see them tomorrow. Now, the next ones must be done on graph paper. Now, do you see this talks about f of x, g of x, and h of x? Well, f of x is that x squared one. That's the one we started with today. Go back in your packet and look at that one. That's our quadratic function. G of x I've defined as an absolute value function. Go back and find that parent graph. That's the v. H of x equals the square root of x. That's the arc looking one. I call it the eyebrow. It looks like one eyebrow.
Oh, it's the.
Okay? So, these are the ones we're going to shift here. And you must use graph paper. I don't want notebook paper because it gets skewed when you're just putting tick marks on notebook paper. So this one, I'm okay with you doing on this piece of paper. This one, I'd like you to use graph paper. And always keep a couple sheets of graph paper in your math notebook. That way you're always ready.
I get research.